Okay, so we're going to look at a quick example for logistic regression, first with binary classification with synthetic data. And we're just going to try and see how all those functions we mentioned in the lecture actually play out. And then we'll look at a more realistic example with multi-class classification. So I'm going to start by generating some data with let's say, a linear decision boundary. So this black line shows the true separating hyperplane. But this data is a little bit noisy, as our data tends to be. So some of the data actually ends up on the wrong side of the separating hyperplane. Okay. So this data is not strictly linearly separable because there is no hyperplane such that all of the orange points are on one side and all of the blue points are on the other side. But that's only because of noise. So you could think of it as if there's some true function, which is like a true decision boundary, that doesn't include the noise, and that's showed here with that black line. Now, we mentioned in the lecture that there's no closed form solution for the linear regression weights, but that you can learn them using gradient descent. So here we're just going to quickly show how we use gradient descent for this binary cross entropy loss function using this gradient update rule. So this is the gradient update rule based on the gradient of that sigmoid function. Okay, so you can see I defined a sigmoid function and a cross entropy loss function that implements this function here. And then here is my gradient descent step, which is based on this rule using the sigmoid and its derivative. And then I'll run a gradient descent. Now I'm defining a tolerance here. So instead of, let's say, running for some unlimited number of iterations, I'm going to run for up to this many iterations, but if my gradient reaches this or less, then I'm going to stop. Okay. And I'm going to start with some randomly selected coefficients. So here's my gradient descent. It stopped at iteration 2359 once the gradient reached this tolerance value. Okay. And these are the values it settled on. Now, what were my true values? Does anyone remember? So my true values were -1, 1.2, and 1. Those were the values I used to generate this line. Now my estimate for the, let's say, weights for the line of the decision boundary are very different. Does that mean my gradient descent is broken? What's going on here? So recall that our decision boundary is defined as, using the equation of a line which is set equal to 0. Now, notice that you can scale this by any constant. So I could use, let's say, kw0 plus kw1x1 plus kw2x2 equals 0. Will it be the same line? Okay, so I can multiply both sides of this equation by some constant k, and it will still be exactly the same one. So my coefficients that I find will hopefully be some scaled version of the true coefficients. So here the black line is a true separating hyperplane, and the red line is the fitted separating hyperplane using the coefficients estimated by my gradient descent. And notice that it's the same line because it's just a scaled version of the same coefficients. Now, does this mean that there are many possible coefficients that logistic regression can choose? Is there a reason it shows this version instead of this version, or is it just totally random? Okay, so there are infinitely many such coefficients that would produce the same linear decision boundary. Does a logistic regression choose randomly, or is there some reason that it chose that particular coefficient set out of all the possible coefficients that produce the same line. Okay. So Ben thinks there's a reason. Do you know what the reason might be? Okay, so that's exactly right. So the reason is maximum likelihood. So remember that the coefficients that it chooses are the ones that maximize the probability of having observed some particular set of y values. Right? What does that mean? Well, we said that the sigmoid function has this kind of shape where the larger the norm of the weights, meaning the larger the magnitude of the weights, the steeper the sigmoid becomes. So let's say this blue line here shows the sigmoid function for, let's say, a large value. The red line shows a sigmoid function for a smaller value of the weights. So it's a larger value of weights means a steeper sigmoid. And remember, the sigmoid is what produces the probability estimates. Okay. So if you have a steep sigmoid, that means for more of your points, you'll have a probability close to 0 or close to 1. For a kind of softer sigmoid shape, you're more likely to have probabilities that are more moderate. What does this mean? Sorry, back here. So here we have kind of pretty cleanly separated data. So we have a fairly clean, let's say, decision boundary. And so we have larger coefficient values. If we had, let's say, maybe more noisy data, then the likelihood of observing, let's say, these particular points would be considered to be less because of that random stochastic noise. And then we would expect to see smaller coefficient estimates because we want to produce smaller probabilities. So essentially, let's see what that does. Okay, so here's the noisier data. And notice that now our coefficient values are smaller because our estimates of let's say, whether a particular point is positive or negative is now less confident. So large coefficient weights means we're picking the version of the separating hyperplane and we're very confident that we can separate the data on either side. So when we estimate the probability of positivity for a particular point, we're very confident in that estimate. Smaller coefficient values will mean we're a bit less confident in that estimate. So let's look at this again. So for a given separating hyperplane, there are many possible scaled versions of it that the logistic regression could fit. And it chooses the one that makes the most sense according to maximum likelihood, which means the larger the coefficient values, the steeper is the sigmoid function in the separating hyperplane, and the more confident we'll be for more of our estimates. Okay. Let's just quickly look at how the gradient descent works. So it's pretty much what you'd expect. The coefficient values converge towards their eventual values. The cross entropy loss decreases, and the gradient goes towards 0. Okay. Moving on, we may recall that once we learn our weights, then we can use these weights to predict the probability of belonging to the positive class for a new test point. So let's take some new test point, and we're going to compute the probability of belonging to the positive class by computing the sigmoid function with the argument z, where z is equal to that equation of the line, right, using those weights we found. We know that if a point is above the line, then the equation w0 plus w1 x1 plus w2 x2 will be positive. And then we expect to see kind of a greater than 50% probability of belonging to the positive class. If that equation comes out to be negative, then we're below the line. And then we expect to see less than 50% probability of being in the positive class. So here's what those contour plots would look like. Right? So the 50% line is at the true decision boundary. As we move farther and farther from the separating hyperplane, we become more and more confident in our decision. So it goes towards 1 or 0 probability in each extreme. How would these contours change if my data was noisier? What would change if, let's say, I change the noise level in the data? So if we change the noise level in the data, well, we know for one thing that the coefficients will be larger, and the coefficients will be smaller. And when the coefficients are smaller, right, the sigmoid becomes less steep, which means that we have more kind of moderate values in this intermediate range for values near the separating hyperplane. So that's what we see here. We still have this kind of 50% line at the decision boundary, but now we have more of these moderate values for points near the hyperplane. Now, we can plot different decision thresholds depending on how we want to penalize different types of mistakes. So if you want to, let's say, get the best overall accuracy, then the 50% threshold is a good choice. But what about if, let's say, you don't really care about accuracy, but there is a very strong cost associated with, let's say, misclassifying a negative point as positive? In that case, where would you set the threshold? So suppose you have a very strong cost associated with false positives. Which decision boundary will we choose? Will we choose the 0.5 point, the 0.25, or the 0.75? So if false positives are very expensive, that means that we want the smallest possible number of blue points to be on the orange side of the decision boundary. So in that case, we might choose a 0.75 threshold. Now, in that case, we'll have fewer false positives, right? So we won't have so many blue points on the positive side of the decision boundary, but we'll also have more orange points on the blue side of the decision boundary. So there's that trade-off. On the other hand, if it's very expensive to miss a positive, so to misclassify an orange point as a blue point, then we might put the threshold at 0.25. So then we might say, okay, for any point where the probability of being positive is greater than 0.25, then let's use that as a threshold to call a positive. In that case, you have a lot more blue points that will be misclassified as orange, but you have many fewer orange points that will be misclassified as blue. Now, since we have this trade-off here, it's a little difficult to think about, let's say, what the overall performance of the classifier is, because the overall performance will also depend on the threshold we choose for deciding whether a point belongs to the positive class. So we can kind of summarize that trade-off by creating what's called a ROC curve. For a ROC curve, you find the false positive rate and the true positive rate for each of a set of potential thresholds. And then you can plot that, and you can also compute the area under the curve. So here's this plot, and this shows you how to use the sklearn ROC curve and AUC functions to compute that for you. So this shows for each potential threshold, where is the true positive rate and where is the false positive rate. So at one extreme, if my threshold is any probability above 0 is classified as positive, well, my true positive rate is 100%, but so is my false positive rate. At the other extreme, if I say any probability above 100% is classified as positive, well, I'm going to correctly classify 0 true positives, but I'll also have 0 false positives. So I'm going to choose some threshold somewhere in between. Now, this dashed line over here shows the performance of a random classifier. So let's say I would just flip a coin. Well, here's what my true positive or false positive trade-off would look like. What would a perfect classifier look like? So if you had a chance to read these notes, so these notes get into some more detail about that. And a perfect classifier will basically look like this. So a perfect classifier is one for which there is no error at all. So even for, let's say, any non-zero threshold, any threshold really, we can get a perfect true positive rate and zero false positive rate. So you can play around with this demo, try adjusting the noise levels and see how that changes the ROC curve and also the area under the curve. Actually, let's do that right now. So let's make this much less noisy. First of all, if I make it much less noisy, what's going to happen to the coefficient values? If the data is much less noisy. So the coefficient values will be larger. The sigmoid will be steeper. And let's see what happens to the ROC curve. Okay, so you can see the ROC curve is now basically a perfect classifier. Now, I just showed you how to compute this logistic regression weights using gradient descent, but you're not ordinarily going to write your own gradient descent because there are libraries that have much more efficient versions of it that can kind of find these weights for you. So we're going to use a logistic regression classifier in sklearn to do this for us. Now, as I said, it works exactly like linear regression, like ridge, like lasso. So we're going to create an instance of logistic regression. We'll pass some parameters. The parameters are related to what kind of procedure we want to use to solve it. Okay. In my next demo, I'm going to explain a little bit more about choosing the solvers. And we're also choosing the tolerance. At what point do we want to stop the gradient descent? Okay, then just like the others, we can use fit to train the classifier, and we'll pass the X and Y data. And in this case, it found the same values as our gradient descent because it's doing the same thing. So this is what our gradient descent found. This is what sklearn found. And we'll have the same probability contours. Now, for the linear regression and also for lasso and ridge, we had a fit function and a predict function for let's say the model instance. For the logistic regression, we still have a predict function. So you can, let's say, predict each of these values, but you can also predict the probability. So for any given value, you can get the class label using predict and the probability of belonging to the positive class using predict problem. So that's what we're using here to produce these contours. And of course, we can also look at the contours for different probability thresholds. Now, there's one more kind of thing I want to show you for logistic regression. With linear regression, we saw that although the linear regression kind of is designed for lines, we can use a linear basis function regression where we transform the features in order to create a nonlinear regression. So in order to perform a linear regression on nonlinear data. Now, the same thing applies to logistic regression. So here I'm going to produce some data with a polynomial decision boundary, true decision boundary. This black line is the true separating line between the classes. Now, if we would fit a logistic regression, you could see this, the score function, which computes the accuracy, shows it only has 80% accuracy, 82%. So it doesn't do very well because it's producing kind of a straight line where the decision boundary is a polynomial. But if we add some transformed features to our model, so if we add, let's say, an x1 squared and an x1 cubed feature to our feature space, and then train the logistic regression on that. Okay. So notice that with this transformed feature space, we can represent a linear sum of the transformed feature space with a linear decision boundary. So now we can take the transformed data, use it to fit a logistic regression, and now it fits our data very, very well. Okay, so this is our fitted logistic regression for the polynomial data using a transformed feature space. Now, what's the disadvantage of doing this? Of course, as you know, adding transformed features reduces the bias. Right? So this here was an example of bias. We have a systematic error between the decision boundary learned by the model and the true decision boundary. On the other hand, adding a transformed feature space will increase the variance of our model. So we have this trade-off here between the bias and the variance. And just like with linear regression, we can use cross-validation to choose a model that has a good bias variance trade-off. We can also add a regularization penalty to our loss function to reduce the variance. So here we described a kind of very basic loss function that's just a binary cross entropy loss. Well, we can add a regularization penalty to this loss function too. And that will also decrease the variance just like it did for the linear regression. Okay, are there any questions on this demo? Excellent. Let's turn to our next demo. So the demo we just did was for binary classification. I want to quickly show you how this works for multi-class classification. And here we're going to revisit the example that we looked at in week 1, the problem of handwritten digit classification. So we're going to read in a data set of handwritten digits. This is a data set known as MNIST. Okay, so I'm downloading this data set here. It's going to take a moment. Okay, each sample in the data set, so every row essentially, is an array of 28 by 28 pixels. So each sample has 784 features, where each of these pixels is a feature. Is that a large number of features? Well, for a logistic regression, it's kind of large, but it's very manageable. So here are some samples of each of the classes. We have a 0 class, a 1 class, a 2 class, a 3 class, and so on, all the way up to a 9 class. And we have many samples of each class. Now, since this is just for demo purposes, I'm going to split this into a small training set and test set. And I'm also going to scale the data. So I'm going to make it so that each feature takes on a value between 0 and 1. This is just because it's just easier to work with knowing what the range is. Okay, and now I'm going to train a classifier using logistic regression. So once again, I'm going to declare a logistic regression instance. Now, I mentioned previously that we have a choice of classifiers, a choice of solvers, so kind of optimization routines that can be used to fit the weights. And in this case, I'm going to use this particular solver because it supports the softmax function. So not all of the solvers that come with the logistic regression class in sklearn support all the potential features. Depending on the solver you choose, it may or may not support regularization. By the way, this one uses a regularization penalty by default. That's why I've explicitly turned it off. So different solvers support different features. Some of them handle different regularization penalties, and different solvers either are or are not capable of multinomial classification using the softmax function. So we're using this one, which does support the softmax function. And just as before, I can create a logistic regression instance and fit my data to. And my data have 784 features and 10 classes. Now, we mentioned that when you have a multi-class classification, what's the dimensions of your weight vector, your weight matrix? So you have K columns, one column for each class, and D rows, so one row for each feature. Or sorry, it might actually be the other way around here. So you have 10 rows, K rows, one for each class, and D columns, so one column for each feature. Now, one nice thing about logistic regression is the coefficients are somewhat interpretable. Okay. So on this plot, the coefficient weights tell us a little bit about probability of belonging to the positive class, the probability of belonging to that class if there is a large value in a particular feature. So remember, every feature here is represented by one pixel. Now let's look at class 0. If an image has writing in the middle of the image, like over here, does that increase the probability of belonging to class 0, or does it decrease the probability of belonging to class 0? Okay, so an image with writing there, that decreases the probability of belonging to the 0 class. So that's why there's a large negative coefficient there. Okay, so writing here makes that Z value smaller, which decreases the probability of belonging to the 0 class. On the other hand, what if an image has writing down the center like this? Does that decrease or increase the probability of belonging to the 1 class? Okay, so that increases the probability. So if an image has writing here, when we compute the Z sub 1, which is the value of Z for the 1 class, any writing here will increase Z sub 1 because that coefficient there is large. Whereas, let's say writing here decreases Z sub 1, so makes it means it's less likely that we belong to the 0 class. Writing over here basically means nothing. Okay. So these logistic regression coefficients are interpretable. We can look at them and see how writing in different areas of the image makes it more or less likely that we belong to a particular class. Now, given the coefficient matrix, this W by K coefficient matrix, we can then take any sample from our test data set. So I'm going to pick a random sample. And then we can compute Z sub K for every class. So let's do that. So this is the Z value for each class. Okay. So that's what we get if we compute Z. So we're taking the weights, which remember we have a vector of weights for each class. And then we have a vector of images. And then we do that dot product there, and we come up with a Z value for each. Now, a strongly negative Z value means that it's more likely that it does not belong to that class. A strongly positive Z value means it's more likely it does belong to the class. So you can see this effect when we compute the conditional probabilities. So now we're computing this G sub K softmax function. My softmax. So we're taking the exponential of each Z and dividing it by the sum of the exponentials. Okay. And now we get an array of probabilities. Let's plot those. Okay, so we can see, for example, the probability of belonging to class 0 is estimated as very small. Right? That's because there was a strongly negative Z value. This probability will end up being very small. On the other hand, we had a fairly positive Z value for class 9, and therefore a relatively large, let's say G sub K. And so actually for this, we estimate fairly high probability of belonging to class 9, 7, 4, or 2. So in this case, the predicted class is going to be the class with the highest probability, which is class 9. So this is not a correct prediction because this sample is actually a 4, but it's going to misclassify it as a 9. Now, I just did this manually so you could see how that z value is computed, and so you could see how that g sub k is computed. But you can use the predict proba function to do exactly the same thing. It will compute the same values. And then you can also use predict to get the predicted class label. Now, just as with our previous example, we can compute an accuracy. And we can also look at, let's say, the true positives, true negatives in each class, or true positive, false positive in each class. So it's conventional to represent this as a confusion matrix. So in this confusion matrix, we have each of the actual values, each of the, let's say, the actual class value in the rows, and the predicted class values in the columns. Okay. And we can see how many are classified correctly. So for example, for class 9, for the actual values in class 9, we can see 252 were correctly classified as a 9. 8 of them were misclassified as an 8. 10 of them were misclassified as a 7. 3 were misclassified as a 5, and so on. You can kind of get a slightly easier to interpret version by dividing, let's say, row-wise. So this tells us the per class accuracy. And we can see here, for example, that a 1 is very easy to classify. We don't make many mistakes on 1s. But a 5 or an 8 or a 9 or 3 is more difficult to classify. We can also see which digits are easily confused. So for example, we can see here that it's pretty common for an 8 to be misclassified as a 1 because this value is pretty high, or it's pretty common for a 3 to be misclassified as a 5, for example, as seen by this value here. Okay, are there any questions?